Welcome to Natural Habitat Adventures Daily Dose of Nature. Today's topic, from mass extinction to dinosaur empire, the End-Triassic event, presented by NatHab Expedition Leader Eleanor Edye. I'm your host, Rob Bess. Thank you so much for being here with us today. Eleanor, take it away.
Right. Thanks, Rob. And hi, everybody. And thanks for joining us on this lovely afternoon to talk about always a popular topic, mass extinctions. So just quickly, who I am, I think a lot of folks have seen me up here before. My name is Eleanor, and I'm one of our Canadian expedition leaders here with Natural Habitat. I have just wrapped up my summer guiding season, so I've recently been guiding our beluga whale programs in Churchill, and before that, our Round Iceland program in July. So happy to be, you know, I was happy to be in the field, but I'm also happy to be at home here talking to you about mass extinctions and getting a chance to connect virtually. So today we are going to be talking about the End-Triassic extinction event. This is one of the big five extinctions that you may have heard of in the past, but it is one of the maybe least well known or least understood. That being said, we talked about some other mass extinctions, and there's always questions anytime that we are talking about an event that happened this far in the past. There's also debate around, which extinctions belong in the quote unquote big five. But we are going to go with the traditional big five and continue talking about these events. So it's sometimes called the End-Triassic, also called the Triassic-Jurassic extinction event. And this event marks the boundary between the Triassic and Jurassic periods around 200 million years ago. This was, as the name might give it away, a large extinction event where in just the marine realm, so in the oceans and in the seas, we lost an estimated 20% of families and about 50% of genera were lost from the fossil record. I've been doing a series on mass extinctions, and I like to look at these not necessarily because I'm a paleontologist, because I'm not. My interest is primarily, in our natural world and in plants. But I also know that when we talk about big global events like this, we as humans have a really hard time understanding geological time frames, so things that happen over a long period of time. And we also have a hard time wrapping our head around whole planet events. So mass extinctions, these big events that happened in the past, give us a chance to look back and understand our planet a little bit better, to get some practice working at geological timescales, which are really hard for any human to truly understand, and also to understand how environmental change that looks small within our lifetime or within an individual's lifetime can shape biodiversity. So I've always had a really big interest in biogeography, which is the study of organisms in time and in space. And there's nothing better for biogeography than looking at when all life or a lot of life disappears from the fossil record. So I have talked about some of the mass extinctions in the past, and I just want to take a couple minutes real fast to kind of bring us up to where we are right now. So first, to talk about what a mass extinction is. A mass extinction refers to a time where we had a loss of global biodiversity with major changes in the fossil record. We have traditionally talked about 5 big extinction events, of which we have already talked about a few of them in our webinars here. So we talked about the End-Ordovician mass extinction, we talked about the late Devonian extinctions, and we talked about the End-Permian extinction. And here today we are talking about the End-Triassic, here shown in the purple. This graph that you can see here is a measurement of biodiversity in the oceans measured by genus level. So just as a quick reminder how a genus fits within our species and families, a species is something like a human or a polar bear or a dog, where we are each individual species and we have relations at a higher level. A genus is a group of species that are more closely related. For example, if we take a polar bear, its closest relations that are currently living are those that sit within the same genus, the Ursus genus. And contained within Ursus are also the brown bear, the black bear, the Asian black bear, and the polar bear. So that's now a group of species. We can take it one level up and talk about families. Then that would be, in the case of the bear, all of our bears. So not just our polar bear, not just our Ursus genus, so our brown, black, and polar bears, but then all bears, including pandas, our spectacled bear, sun bear, everything that is contained within that family. So when we're talking about removing a genus or a genus going extinct, we're talking about a huge loss, so multiple species. And when we're talking about a family level extinction, we are talking about tremendous losses. So imagine just wiping bears off the planet, or imagine wiping canids off the planet. So losing foxes, losing dogs, losing wolves and coyotes. That would be a family level extinction. So it represents a huge loss of biodiversity. Here, I mentioned that we had about 20 to 30% losses at the family level for this extinction. This is, 20 to 30% might not sound like a lot, but it does represent a huge number of the species. So when we look at these big drops that are shown on this graph, because these are genus level drops, each of these big drops represents at least 75% of all the species being lost at that point in time. So all of these were tremendous, massive events that affected global environments across the planet. Now, when we were talking about these before, we talked about all of these plus one more. We also talked about the Great Oxygenation Event, which is kind of the big five plus one. It is the least understood for sure mass extinction because it happened way, 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 way back in time, back before oxygen was even part of our atmosphere. The Great Oxygenation Event was a change in our atmosphere that was primarily nitrogen and carbon dioxide based to one that is now nitrogen and oxygen based. So it's like all of the organisms that evolved prior to that point required low or no oxygen, and suddenly the whole atmosphere shifted, and we had new evolution and new organisms coming up after that time. It might not sound like it was prior to that a very hospitable environment for you or me, and it wouldn't have been. We would have died. But all the organisms that lived prior to that major change were very hit by the oxygenation event. So first time that we saw real global change. The first of our big five mass extinctions that we talked about was the End-Ordovician. So this was around 444 million years ago. At this point, we had a couple of pulses of extinction that collectively added up to over 85% of all species lost. This was a worldwide extinction event. All habitats were hit and was probably our second most severe mass extinction, second only to the end Permian. Now, this was an interesting mass extinction, and I'm going to just remind us of what the causes for these extinctions were, because by now, as we start getting into our mass extinction number 4, you're going to start to notice that there are some general trends. So at the End-Ordovician, we had a lot of coastal habitats, a lot of shallow seas. A lot of our diversity at that point came from the fact that these seas were separated by deep water oceans. So we had all of these diverse pockets that were not connected, and a species, in the northeast might have had a relation in the southeast, but they did not cross over, they did not combine. We had diversity because of all these different regionalized habitats. At the End-Ordovician, we had a lot of change happening. One of those things that happened was a change in the global sea level. So we lost somewhere between 50 and 100 meters of sea level change. So a drop of around 80 meters, around 250 feet. This basically dried up and exposed all of these shallow water continental shelves that we were just talking about, all of these habitats. And because these were all separated, we were not able to have replenishment from the other ones around the world. So we had a big change to get really cold where the sea level dropped. And then we immediately had a pulse where everything warmed back up before there was a chance for everything to reestablish. So we had everything got real bad in one direction, then everything got really bad in the other direction, and most things died. That was the End-Ordovician. The late Devonian Devonian was different again. So in the Ordovician, we had just sea habitats. Organisms had not really made it onto land yet. But by the late Devonian, we had our first trees starting to pop up. This was, surprise, surprise, another really bad time to be alive. We had a loss of about 80% of animal species. Almost all of the vertebrate species that were alive at this point died. And we had a loss of 20% of animal families. So most of our losses here were of our bigger organisms. There were some stressors that we could recognize. So the possible stressors that are recognized for the end Devonian were extreme volcanism, so lots of volcanic activity, meteorite impact, there was evidence for that, as well as sea level change. One more time. And part of the reason that we think the Devonian was so interesting is that one of the stresses was also to do around the fact that we suddenly had trees and had never had trees before. When you add in basically a whole other set of organisms taking advantage of habitat that wasn't habitat before, they actually drew up a lot of carbon dioxide from the atmosphere. It caused cooling. The cooling, again, changed the sea level, killed the reefs, and then we had volcanism as well. So it was, again, a time of like big, big, big shifts with a lot of massive stressors working at a global scale. And then the last one we talked about most recently was the end Permian extinctions. The end Permian is also known as the Great Dying. So at this time, about 95% of species became extinct in the water, and about 70% of all land species went extinct. So it was the closest our planet has ever come to everything just giving up and dying. The most extensive extinction event ever recorded in the rock record. Why did this one happen? Oh, it was a whole bunch of things happening all at once. Again, we had extensive volcanism. We had sea level change. And there were early theories around a meteorite impact as well. But we have really landed as the end Permian extinctions being primarily due to these extensive volcanic regions known as the Siberian traps, that caused initially global cooling as all of those volcanic aerosols cooled down, and then global heating as the aerosols dispersed and the carbon dioxide in the atmosphere started to warm it up. We then got acid rain, which gave us acid oceans, which gave us great big dead spots in the ocean with not enough oxygen. There were widespread wildfires and toxic gases in the atmosphere. Any one of these things would have been bad news. When you add them all together, you end up with nearly everything on the planet dying. So that is where we left things. At the end of the Permian, at this point around 250, 255 or so million years ago, what comes after the Permian? Well, we are now moving on to the Triassic, where we are right now. So you've already seen that we've kind of set ourselves up for, I mean, anytime we talk about mass extinctions, feels like sometimes we're setting them up and knocking them down because everything we're going to talk about is probably going to die. But we're right here. We're right after the Great Dying. We're right after the end Permian mass extinctions. Between that point and the end of the Triassic, there is not a whole lot of geological time. Like 50 million years sounds like a long time, but in terms of like recovering from a mass extinction event like that, recovering on the oceans, recovering on land, you got to get to it pretty quickly because there's a lot to do. So this is what the Triassic looked like kind of midway through or towards the early side. This is still a time of Pangea, so all of our continents were together. We had the Panthalassoc Ocean, which wrapped around the outside, and then the Paleotethys Ocean, also called the Tethys Sea, was kind of in the middle there. So it was salt water, but it was more protected from the ring of continental crust around it. So sounds like a great time to be around. It was geologically relatively stable for part of it. We had some mountain building episodes. We had some volcanism, which we'll talk about in a bit. But overall, things weren't moving around a whole bunch through the Triassic. Pangea was what we got, and Pangea is what we kept all the way through the Triassic. What happens when you have kind of all of your continents all blocked up like that is that you don't have a lot of oceanic habitat. A lot of our most diverse parts of our oceans are along the coastlines, and you can see that all the coastlines here are smushed together. So your coastline habitats are more limited, which is going to limit the species that you get. But you also have a lot of, ocean circulation happening, and you tend to have drier environments when you have less coastline because you don't have the opportunity for the moisture from the oceans to make it all the way into the center of the continent because the rain just can't travel that far. So here we are, we have kind of a hot land. It's relatively dry, especially in the center of the continents. We have all of our continents smushed together. We have very few coastal regions relative to what we have now. How are we going to rebuild this planet? And what have we lost? So remember, we have lost a lot of things in the Permian. We finally lost our trilobites, those big organisms that we all love to collect fossils of. We lost a lot of corals, especially the horn corals. We lost a lot of ancient mammal relatives like gorgonopsids. We lost some of our a bunch of our fish species. So Triassic is really a time where life is retaking the landscape, starting with some of our early taxa. So this here is Chloria, which is a type of bivalve. So Chloria is what is called a disaster taxon. We see disaster taxa in the fossil record sometimes when something really bad has happened, a lot of things have been wiped out, and you have what is, biologically kind of like a weed, where they go in and go, look at all that empty habitat. I'm going to take advantage of that. So we have, if you think of weeds in your garden, they're just taking advantage of that empty habitat of all that nice empty earth that you have created for them. So they are good at moving in quickly, at reproducing quickly, and often taking advantage of maybe what we call marginal habitats. For us as humans, that might be things like gravel parking lots. But in the case of Chloria, it was an ocean floor where most things had been killed off, where oxygen levels were very low, and where nutrient levels were also very low. What do you get? Well, you get the only thing that can survive in those conditions, like Chloria. So it was able to live in those low oxygen waters from shallow down to deep water habitats, and they were therefore good at taking advantage of the conditions that existed after the end of the Permian. So those conditions, those really bad conditions, did persist for a while into the Triassic. That recovery was not immediate. After you kill everything off, things do take a while to recover. So we're looking at that recovery. What else recovered in the oceans? Well, eventually, after Chloria did its thing for, 10 million years or so, picture 10 million years of the only things growing in your oceans being a single species of clams. That's basically what you were looking at. But things did recover. The oceans became oxygenated again. Things did recover, and we started to see life starting to re-radiate. So we'd lost a lot of things. We'd lost a lot of ammonoids. We'd lost a lot of brachiopods. We'd lost basically almost all of our corals. We had all of these empty niches that then our organisms had to re-evolve the ability to fill those niches. And one of the things that is new on the scene in the Triassic are the stony corals. So these are the scleractinian corals. We have not seen them up until this point because they haven't existed up until this point. The stony corals are the ones that we still have building our reefs today, like certainly different species, but the group as a whole got its start in the mid-Triassic. All of our prior reefs were built by things like rugose corals and tabulate corals, which are now extinct. We have left those all behind. They didn't leave the Permian. Corals had to re-evolve as a type of organism. So they just decide, I'm being a little silly here, but something decided that was a great place to live, and they re-evolved a coral lifestyle. So this was big news in the reef community. We get our first appearance of our modern corals, and they are starting to rebuild reefs. What else was happening in the oceans? Well, we also had the start of some big reptiles starting to move into the ocean. So our first ichthyosaurs and our first plesiosaurs also appeared in the Triassic. We actually don't have a really great understanding of where these came from. We didn't have any transitional forms. We didn't know if they like evolved from the water or evolved from land. But there were some recent studies suggesting that they probably evolved from a land-dwelling amphibian that was present in the early Triassic that then moved into the water and evolved into the plesiosaurs and ichthyosaur life forms. So that's what we're seeing in the water. We are seeing recovery. Our fish are starting to recover. Our corals are recovering. All of our, our algae is recovering. Everything from the very bottom up to the top is recovering and starting to grow into a functional ecosystem again. Well, what about on land? Well, land has changed significantly after the Permian. Remember, in the Permian, we killed off about 70% of the land species. In the water, it was a whole lot more than that. So water is basically, the water habitats are basically starting from scratch. And on land, we have now moved into what we call the age of reptiles. So we sometimes call these periods of time not by the names that we've given them, but what is kind of dominant in the fossil record and dominant on the landscape. So we've talked about the age of fish. We killed off all of our fish, not all of our fish, but we killed most of those off. They had to, again, re-evolve to fill those niches. We are now talking about the age of reptiles, not the age of dinosaurs. We'll talk about dinosaurs in a second, but the age of reptiles. So in the Triassic, there were three main groups of land-dwelling animals. We had the dinosauriforms, we had the therapsids, and we had the crocodile ancestors. So let's talk about those for a second. So really what you're seeing here is a movement towards what we call an amniote lifestyle. So instead of being things like an amphibian or any animal that then needs to go back to water or a water habitat to lay an egg, we have the evolution or continued like development in the evolutionary lineages of animals that use that are able to either give live birth later on, right? So these are the ancestors of the mammals, or ones who had hard-shelled eggs that were adapted for land. So those are the groups that we see popping up. We see a lot of early reptile experiments. So in the Triassic, we had the first turtles popping up. We had the first lizards, true lizards. We had the first pterosaurs, so flying dinosaur-like animals. We had the first earliest representatives of the lineages that gave us frogs and salamanders. We had the ancestors of the crocodiles. Now, you'll notice as I'm saying these, ancestors of this, ancestors of that. Remember, we're setting these up to knock them down. We're not seeing most of these animals later on because what we're seeing here are the precursors to what ended up surviving into the Jurassic. So what you can see here on the screen is one of our first actual dinosaurs. So not just a dinosaur form, like a dinosaur relative, but this is one of our first theropod dinosaurs that did evolve in the Triassic. This is Coelophysis, who lived around 215 to 200 million years ago. So it was cut off at the end of the Triassic as well. So it's a very small theropod dinosaur. You can tell looking at it that it was a predator. And this was one of the kind of the lineages. So the actual dinosaurs and the cousins of the dinosaurs were one of the three groups that were dominant on land at this point. The next one is the therapsids. So therapsids include a whole bunch of kind of early mammal relatives. In this case, you're looking at a type of cynodont. So they are the cynodonts. Some of them went on to survive the Triassic extinction. Here I am giving things away, but many of their relatives did not. So we're looking here at some of our earliest lineage relatives, presuming that you're a mammal watching this right now. So this was one of the ones preserved because it was a carnivore at the time. The fossil record suggested it was about the size of a fox, might have had hair, maybe not. But probably due to the size of its dentition and what was around at the time, it fed on like insects and invertebrates. Okay, so we saw our dinosauriforms. We're looking at our therapsids, or early mammal relatives. Now let's talk about who is really dominant at this point. And this would be the crocodile line relatives, not true crocodiles yet, but those who are relatives of what we now know as crocodiles and what have gone on to become crocodiles. And even within this group, you have a bunch of crocodiles, ones that went on to give us today's crocodiles, and then you have a bunch of other things that are still acting like crocodiles anyway. So when we look at them in their kind of evolutionary record, we can collectively call them archosaurs. If you want to get, learn a new word today or get fancy about it. So these are a bunch of species, all closely related, that are also related to then their descendants being crocodiles. They were related to dinosaurs. They were also related to, of course, then birds. But the only ones that kind of survived through this extinction period were called the crocodilomorphs, so the ones that eventually gave rise to the crocodiles. So here's one of these bad boys that we're looking at here. It's an artistic representation of one of these archosaurs that was taking a crocodile life form. You can see it looks an awful lot like a crocodile, probably behaved an awful lot like a crocodile. And then you get some fun ones too. So this is another archosaur, also probably closely related to a crocodilian. This is Desmatosuchus. So another one from kind of the late Triassic. In this case, this one was found around the Texas area. So kind of a cute little archosaur you can see there. But the life forms, they weren't all crocodile-like. Some of them were just still archosaurs, but have evolved other ways of being as well. So this was another archosaur, but this one, as you can see, is a flying one. So at one point we had flying insect eaters that were lizards. And if you look at how it's flying and its leathery wings, it was actually not built from its arm bones, which is how we know of all of our wings today. Like whether you're talking bats or birds, it's all like changes in the arm bones. But this particular lizard actually took a whole different strategy and extended its rib cage outwards and its skin around the rib cage. Really kind of interesting. We don't see any of that these days, but this did evolve a few different times. There were some other relatives of this guy around the same time that seemed to have the same strategy of using ribs for wings, or at least to, if not wings, as an aid in gliding. And then probably when I say crocodile relatives, you're going to think this one. This is Carnifex, also called the Carolina Butcher, which is a really great, terrible name. So depending on how much time you spend with popular science magazines or reading some of the journals involving some of our early reptile studies, you might have seen something at one point going, early crocodile relatives might have walked on two legs. So this is the kind of thing that we're looking at here. So even our earliest crocodile relatives, they took many, many different life forms, right? Some were small gliding insect eaters. Some were more typical of the crocodile life form that we see today. Some acted more like what we might picture as a dinosaur, because the crocodilians and the crocodilomorphs and all of these archosaurs were the dominant life form. They filled all the niches, right? They were the predators, they were the herbivores, and they were all reptiles, and they were all relatives of what would eventually down the line give rise to the crocodiles. So this was truly the age of reptiles while we still had, our dinosaur forms, while we still had our early mammals. It really was a reptile-dominated ecosystem and a reptile-dominated world. On top of that, it does seem to have been a time of the planet where we had a very heavy predator load, with some predators eating other predators instead of eating herbivores. So there was for whatever reason, and there's still like a lot of debate about this, a lot of studies ongoing, it does seem to have been a time with heavy predator load, and even if you were a predator, you still weren't safe from being eaten. So sounds great, right? I mean, it sounds great if you're a predator, maybe less good if you're a prey. We have this beautiful world that has finally rebuilt itself post-Permian extinctions. We have a functioning land ecosystems, we have a functioning ocean ecosystem. Sure would be a shame if something were to happen to it. And boom, we're going to now go through and knock these organisms down. So let's first talk about what happened, or what we think happened, and then about what was actually lost from the ecosystems and the planet here. So remember I said that the Triassic came to an end around 200 million years ago. I went through kind of our earlier mass extinctions to remind us of some of the causes of those, or what we think the causes were. So the suggestions for the End-Triassic extinction tend to be pretty similar, right? Evidence of massive volcanic activity, evidence of asteroid impact, and evidence of sea level change, right? So with this, there's of course still lots of debate. We're talking about a period of time 200 million years ago. Anytime that we're talking that far back, we're talking big chunks of time, right? It is impossible to look at a single year in the fossil record. You have to look at a large portion of the period of time that went on to add to that particular fossil record at various locations. So what we do know about the End-Triassic is that it was a long period of time, but that long period of time may have just had a very high extinction rate. Or was it a single pulse, or was it multiple pulses? That is something that we're not able to answer at this point. We do not have the granular information to say, was it one long period of time where a lot of things were just like dying off more often than they were being replaced? Or was it multiple pulses of some kind of catastrophe? There's evidence in both, in favor of both. So we'll start off with the one that we are at this point pretty sure that actually had nothing to do with the mass extinction, but it's still always pretty fun to talk about asteroid impacts anyway. So this is the Manicouagan crater in Quebec in Canada. It is a crater impact zone. You can see it's about 100 kilometers in diameter, and it stands out really well in the landscape. You can go onto Google Earth and see it because it's also now used as a reservoir for hydroelectric power generation. Now, the dates of when this meteor impact happens seem to line up with a lot of the extinction time, except where it doesn't. So there's evidence kind of pushing it one way or the other anyway, but we know that the structure was created around 210, 250 million years ago. The impact, the meteorite itself that hit was probably around 3 miles or 5 kilometers in diameter. And there is certainly evidence that the dust from a meteor impact of a rock that big would have disrupted photosynthesis around the world, right? So you have a lot of dust being flung up into the atmosphere through something like this. You get multiple years-long winter because photosynthesis just can't happen through all of that dust. Things cool down, and it takes multiple years for that recovery to happen. That probably all by itself wasn't enough to cause a mass extinction, but when we look at all of these things together, could it have been another part of it? Absolutely. Like anytime you have a stressed system, adding more stresses will, of course, have an impact as well. Now, it was a warm time in our planet's history, so our temperature there is the upper blue curve. That Permian that we talked about before is right before the Triassic, and you can see that in the Permian, we went from globally relatively cool to whoop, shooting real hot, real fast there, which is part of the reasons for the Permian being such a difficult time to live through. And then in the Triassic, you'll see there's no big changes, just some wibbly wobblies. But overall, it was pretty hot with relatively high levels of CO2. And then here's the Triassic sea level curve, and you can see that there are some oscillations in the early Triassic, and then a prolonged long shift to a drop in sea level over the late Triassic. Again, would that have changed things over such a long period of time? We don't know, but well, okay, yes, it would have changed things, but would it have caused a mass extinction all by itself? Probably not, but when you have big changes like that, it changes the coastal habitat, it changes nutrient availability, it changes the sunlight, how much of it can penetrate down into the water, it changes the ocean currents. But as you can see, looking back through the graph, we have a lot of other times in history where sea level changes happen without killing everything on the planet. What we can say about sea level change, that it's probably like the meteor impact, not the cause, but probably created some stress in the environment. And let's talk about now what we're pretty sure was the ultimate cause, even though the sea level change and the meteor impact would not have helped. And this is the volcanism that we talked about. So the extensive volcanic region that probably caused the Triassic-Jurassic mass extinction was caused by this massive volcanism in this orange zone that you can see here, labeled as a rift zone, called the Central Atlantic Magmatic Province. So we first started getting evidence of this about 30 years ago, but it's taken some time for widespread acceptance of this being the ultimate cause of this extinction event. I'm going to tell you how much lava came out of this rift zone. So I'll start by saying a rift zone is where we have plates spreading, so we have the Earth opening up and lava coming out. If you think about Iceland, that is also like a rift zone on a very much smaller scale, for example. But in this rift zone, the Central Atlantic Magmatic Province rift zone, which eventually went on to open up and give us the Atlantic Ocean, you can see that this is what split Pangaea apart. This rift zone produced between 2 and 6 million cubic kilometers of lava. 2 to 6 million cubic kilometers of lava. That is an unbelievable amount of volcanism. It's an unbelievable amount of new rock being produced. And we don't exactly know over how much time this happened, but we think it was pretty quick. We think it was over multiple pulses, about 4 pulses over about 600,000 years. Geologically speaking, that is incredibly quick. If you want to liken it, like that is, it's while being relatively quick, it is still more time than humans have existed as a species. So again, 2 to 6 million cubic kilometers. If you picture a kilometer, so about 2/3 of a mile in a cube, that's a lot of lava all by itself. Millions of those. Just an incredible amount of lava. You can still see evidence of this in various places around the world. One of those places is in Morocco, where you can still see those basaltic lava piles, so that dark layer in the mountains here. So that's one of our most studied areas of those basaltic lava flows, because remember, it happened on either side of the Atlantic. And then on the other side, you have evidence like the Palisades along the Hudson River. So these look a little bit different because the environment is now different, but they were also underground channels of magma that have now been exposed through erosion. So these pulses, I said they probably occurred multiple times over about 600,000 years, but there's also other studies that suggest that all of this could have happened in as little as 20,000 years, which is, again, like it's a blip of time in the geological time frame. It sounds like a lot to you and I, because we can't really picture 20,000 years very easily. But if you picture your whole world being taken over by lava, that's maybe a little easier to picture. So when you have that much new lava and new rock being exposed at the surface, there's a whole bunch of things that happen that we know from seeing volcanism in current times will happen. So when you get a big volcanic explosion, and those of us who have lived to, Mount Pinatubo or Mount St. Helens, you know that there's usually a period of short-term cooling because of the sulfur dioxide that gets released from the volcano. It forms aerosols, solar radiation, sunlight from reaching as well to the surface of the Earth. So it cools things off in many areas, especially our polar areas. You might get years where you never get a summer after a big volcanic eruption. There's evidence at the End-Triassic for severe volcanic winters with temporary evidence of glaciation. But then you get the other side of it. So after you get that short-term cooling, you get your next stages, which are going to be long-term warming. So you have a lot of carbon dioxide that is put out by these volcanoes, and especially with a huge, huge volcanic event like this, you get a lot of CO2 in the atmosphere, and the CO2 is going to start to warm things up. And as you warm things up, you get other things that happen now, right? So you've warmed the planet, wildfires become more frequent, and there is evidence in the fossil record for tremendous wildfires. With the wildfires and with the warming, there's also big rain events. So we have much larger rainstorms than had been seen previously. Combined with the wildfires, we saw incredible soil degradation. So evidence of incredible topsoil loss, which makes then our continental regions less able to support life. All of those nutrients then get pushed by the rain into the ocean. And all of that nitrogen, the phosphorus, the potassium, all ends up landing in our coastal regions. Just like we see today, that gives us often a lot of algal blooms. And as we have big blooms of algae that then die, they take up a lot of oxygen in the that's present in the system. So we start to see dead zones popping up in the ocean. On top of that, we have all of that CO2 in the atmosphere. It's going to then start to acidify the oceans as well. So the pH level of the oceans is going to start to drop. So we have dead zones in the oceans. We have our oceans, dead zones with no oxygen. We have our oceans starting to become acidic. And we also have evidence of euxinia, which is high amounts of hydrogen sulfide. And this was probably present from the sulfur dioxide that was in the atmosphere, then precipitating in the rain. So we had sulfur bacteria that then were using hydrogen sulfide to feed in the water column, making things even worse. We saw that. We saw all of this global warming. We saw disruption of the ocean circulation. All in all, it was not a great time to be on the planet. To give you an idea kind of what we're talking about for carbon dioxide emissions, the record that we're able to access shows us these distinct pulses of carbon dioxide following those various pulses of magnetism, at least a couple of which either one of those like pulses would have produced enough CO2 emissions into the atmosphere at the same level that humans produced in the entirety of the 21st century. So we're pretty good at pumping out carbon dioxide. This volcanic event pumped out multiple times within presumably a fairly short period of time, again, like thousands of years, but that's geologically very short, increasing the carbon dioxide in the atmosphere quite a bit. So what happened? Well, let's knock them down. What changed in the ocean? So these red marks along Pangaea here, and you usually see Pangaea the other way, but here we're talking about the oceans. So those red marks are the coral colonies that were present during the Triassic, basically none of which survived this extinction event. So many things were wiped out. 96% of all coral genera were wiped out. Corals are basically gone except for the very northernmost reaches of the ocean, with over 30 families having gone extinct. The collapse in the reef community was complete. So we had all that ocean acidification due to excess CO2 in the atmosphere. And all of those ancient, not all of the ancient reefs, many of them can still be seen in the fossil record in the Alps, for example. So they all ended up being moved upward due to the way the continents moved around. So the ammonites were nearly wiped out. All of the reefs were pretty well wiped out. And then we had these guys here being a type of coral that we no longer have. So this is a type of cnidarian. It's the conularia, and it no longer, if it doesn't look familiar, it's because it no longer exists. So that's what it looks like up on the top right there. Pretty cute little sessile feeding organism. No longer around, right? So we got rid of all of our corals. Once again, we've done this before, and Here we still kept a few of them, but we got rid of basically our whole coral ecosystem. What else did we do? Well, here's probably one of the biggest losses that you've never heard of. These are the conodonts. So they are small fish-like organisms that kind of resemble today's hagfish. They are vertebrates, so they were one of the first vertebrates to evolve, and they stuck around for a very, very, very long time. They survived 300 million years in the fossil record, and they survived every earlier mass extinction that we talked about. They are very useful in the fossil record because their little jawbones there are used for dating the various strata, because they all look a little bit different, and you can tell when your rock sample is from based on the conodont fossils. Well, after 200 million years ago, they were no longer around. So they were around for a very, very, very long time until they were no longer around. And then still in the oceans, marine reptiles had a substantial drop in diversity. But the only group that went extinct were these guys here, the last family of placodots. So up on our top left there, that was Placocheilus, flat plate turtle. Very handsome little guy. Not that little, they were about 3 to 4 feet long. And we lost basically any relative of an ichthyosaur or a plesiosaur that wasn't itself an ichthyosaur or a plesiosaur. So the ichthyosaurs and the plesiosaurs crossed over the extinction boundary, but most other things did not in the marine reptile family. Now, this was also the time in the oceans, just as we saw a big turnover in the type of life. So this here is just, it's a conceptual thing of our 3 great evolutionary fauna of marine mammals. So our first animals that evolved in the ocean, we called the Cambrian fauna. They peaked and then declined over time until we lost our last ones at the end of the Permian. What replaced them was the Paleozoic fauna that were kind of typified by the age of trilobites. And we still have Paleozoic fauna around. It's not like they're all gone, but you can say they went through a massive drop at the end of the Permian and another drop at the end of the Triassic. After the Triassic, they never really sprang back to any kind of dominance. They were replaced fully in all of most of their niches by the modern fauna that we see here. So you can see that the modern fauna increase in biodiversity, and our Paleozoic fauna, while still around, have essentially been replaced in our oceans. And it was really the end of the Triassic that marks this turnover time between our old fauna and our new fauna. So what else was lost? Well, on land, the terrestrial animals were much more affected than the marine animals. So I already said that lots of marine animals were lost, but we had major turnover in the terrestrial tetrapods, like our amphibian relatives, our synapsids, so all of those ancient mammal relatives, our reptiles, our early dinosaurs, our early lizards, and our early crocodile forms. Lot of turnover. The estimate is that about 50% of all of our terrestrial 4-legged animals went extinct at the end of the Triassic. So this particular guy here that we're looking at was an early amphibian relative, gone. Anything that you've ever seen in a dinosaur museum or in a dinosaur book that looks like a dinosaur through the Triassic or had a dinosaur lifestyle or made you think, hey, is that a dinosaur? Only to be corrected by a 6-year-old that it's not a dinosaur, it's an early reptile. All of those things are gone, right? Anything that had that type of lifestyle or that type of appearance that didn't make it through the boundary, only the dinosaurs did. So we had that kind of reversal of who was on land. So all of our early dominant reptiles, they got knocked to the back, and it was the dinosaurs who kind of coasted through the mass extinction. So it's not that, again, we don't have reptiles, but they were very, very much knocked back in their dominance level at the end of the Triassic. On land, we did also have some losses in the plant communities. And this is a major knock for things like the ginkgos and the ginkgo relatives. So you might know ginkgo biloba, you might take it as an herb or see it at the pharmacy in your natural supplement section. So we have one plant left on this planet, ginkgo biloba, that belongs to this group. Before the End-Triassic mass extinction, we had many of them. They all looked a little different, but they were all relatives of our ginkgo biloba today. And the only one that kind of straggled across the boundary was an earlier relative of the ginkgo biloba that we have now. A lot of trees died, and we had a big changeover in what we had on the land. So we left behind a lot of those kind of quote unquote earlier plants to change over to our next wave of evolution. Now, immediately post apocalypse, the ferns did pretty well. Ferns spread by spores, so they tend to do pretty great in a crisis. They like to grow on dead things. They spread their spores pretty easily. But then as the fern wave declined, they were replaced by things like gymnosperms, like ancient relatives of pine and spruce that had not yet found their way onto the scene before now. And this is the not the end of the story, but where the End-Triassic mass extinction takes us is removing things from the landscape that allowed all of that empty niche space to be taken over by the dinosaurs, which then would go on to dominate Earth for the next 160 million years. The dinosaurs did pretty great. They had a pretty good run of it, and they have been on land a whole lot longer than they had been on land a whole lot longer than we have. So dinosaurs experienced this major radiation post Triassic mass extinction. They filled a lot of the niches that were vacated by the victims of the extinction. And then the other survivors from this time were the crocodilomorphs that also underwent a rapid and major adaptive radiation. So the crocodiles, the early crocodile relatives squeaked across the boundary. None of their relatives made it. The early dinosaurs squeaked across the boundary and basically took over the Earth. And then our ancient, mammal relatives also squeaked across the boundary and continued to radiate in the early Jurassic, but they were not the dominant life form on the planet, really the dinosaurs there. In the marine environment, the large marine reptiles continued to dominate. So remember I said that really the ones who came across the boundary there were the ichthyosaurs and the plesiosaurs. They continued in the Jurassic, leaving all of their other relatives behind that did not make it. And just to call out the plants, a cool thing that did happen pretty rapidly in the Jurassic was the evolution of diatoms. The coolest thing you've never heard of, probably, unless you're a gardener who likes to use diatomaceous earth in your garden. So this is a form of algae, and it evolved in the Jurassic. And specifically, it's a form of algae that we now have in our polar ecosystems. It goes on to form the base of the polar food chain, giving us things like polar bears. But also, if you're using it in your garden, it's because diatoms have a little glass shell around them, and they grow in their shell, and then when they die, their little glass shell stays behind. And if you sprinkle it in your garden, you can control your pests naturally with these little tiny glass shards. The recovery of algae was a major part, and then of course recovering coral as well. So while coral was very, very hard hit at the end of the Triassic, the evidence suggests that it was also relatively quick to recover once conditions improved. So the ones that survived and radiated, and they are the relatives of our living corals today. So here's our beautiful Jurassic landscape, including our ancient relatives of pines, our dinosaurs, and our early birds. And this landscape would go on to really be the dominant type of landscape for a very, very long time until our final mass extinction, the end Cretaceous mass extinction that doesn't happen for millions, like 120 or so million years later on. So good time to be a dinosaur. And with that, I will just kind of leave us with the thought that we often talk about the End-Triassic when talking about analogs to today, because a lot of the things that we talked about, like with ocean anoxia, um, acidification of the oceans, and increasing CO2 levels in the atmosphere, have happened at similar time frames to what we're talking about now. I mentioned this for the Permian as well. So we do often use the analogs of what happened at the end of these kind of mass extinction events for some of our current conditions on Earth. And that's not necessarily to say it's all a bad news thing, but as long as we are taking knowledge and learning from this, we have a lot of evidence that kind of tells us what's good for the planet and what's really harmful to biodiversity. Um, so I'm happy to see that I've left a few minutes for questions. So I'll hand things over to Rob.
All right, Eleanor, thank you so much. So before we dive into the questions, I would like to remind everyone that if you do have questions, feel free to submit them via the question field in your control panel. Just go to the upper right-hand corner and click on those three lines. It'll open up the menu, go to questions, and that's where we will be working from. All right, so let me ask you this question. Do you think that evolution follows a gradualism or a punctuated equilibrium pattern? Could some organisms evolve following one pattern and others follow the other?
Ah, what a wonderful question. I haven't thought about punctuated equilibrium for a very long time. So the concept here is kind of talking about exactly as you say, like whether these evolution happens gradually, like um, an analogy to that or an explanation for that would be like gradual modifications in our genome over time that gives us something different at the end, or does it happen quite rapidly, basically causing evolution to take massive leaps in a short time, punctuated by long periods without change? And from my knowledge, and I'm not an evolutionary biologist, I just love talking about these things and love learning about these things. From my knowledge, we do have evidence of both types of evolution occurring. We've seen very fast evolutionary changes in even in human lifetimes. For example, like the example of Darwin's finches being able to re-evolve the size of beak needed for a particular food source over time. We see things happening very slowly as well. So my answer is it's probably both, but seeing things in a human lifetime is very, very challenging. And when we go back and look at prior information, whether we're looking at fossils or whether we're looking at old genomes, we're going off of secondary information. And for all we know, if we're looking back in the fossil record, maybe one day um, a dinosaur was born with pink feathers, and every dinosaur after that point was born with pink feathers, but we'll never know it because we don't have any of those pigments that are saved in the fossil record. And that's obviously not a true example, but there's things that we will never know about, or at least we won't know about with our current way of understanding things. So with what we can know with our human level knowledge, my understanding is that it does take both shapes, but you have to expect that when you have the planet kind of wiped out like that, that it does leave a lot of empty niches, and that when recovery happens, it happens usually in a slow beginning because conditions are still quite poor, but then we see radiation happening very quickly after that once conditions have improved, which tells me that like evolution probably can work very fast at some points, but not at human timescales.
Great, thank you for that wonderful explanation. Um, so you showed a poster of the dinosaurs of the Jurassic period. Was there a
Yeah,
Triceratops in that poster?
was there? Let's take a look. Uh, I don't believe that there was. I don't see one.
Uh-huh. Very
And I will
interesting.
say that for best knowledge of dinosaurs and when they happened, you really do have to ask a 6-year-old. Um, I I like dinosaurs, but I don't think anybody can like dinosaurs as much as a 6-year-old likes dinosaurs. I've been schooled on things many times when talking to 6-year-olds about dinosaurs.
They certainly do love dinosaurs, don't they?
They do.
So, with all the climate changes and previous mass events, do you think the Earth will survive the much faster climate changes imposed by people today? And part two, are we headed towards another event?
Well, that's the $1 million question, isn't it? I think that when we are talking about these kinds of events, for example, taking the Central Atlantic Magmatic Province, right? We talked about how there were probably 4 main pulses over 600,000 years old, that each one dropped as much carbon dioxide into the atmosphere as much as humans have in the past 100 years. For us to use that, as that's a very helpful analog, but for us to use it, we will never know if that pulse happened in, 5 years. Did it happen in 500 years? Did it happen in 5,000 years? Because we can't get that granular in how we analyze rock samples. It's impossible to get any closer than that when you're talking 200 million years ago. But if we're talking about other rift zones and how things have built up over time, like we have seen events where large amounts of volcanism has dropped a huge amount of carbon dioxide into the atmosphere at once. Kind of analogous to what we're doing right now. It has very much affected the planet, and it's affected the planet at a global scale, both the atmosphere, our land-based ecosystems, our marine-based ecosystems. But what we can also say from looking back at these mass extinctions is that the planet will usually recover. It's not going to recover the same way. Things are going to be different, but they're going to be different in a semi-predictable way, right? So as soon as you remove the thing that's causing the problem, in the case of the End-Triassic, it was probably that combination of sea level change and excess carbon dioxide and meteor impact. Once that stops happening actively, the Earth is pretty good at regaining a relative level of homeostasis. Now, the Earth has kind of gone up and down in temperature over time, but what happens, for example, with all that new rock formation is that it gets weathered, and as it weathers, it absorbs carbon dioxide. So the Earth kind of it has somewhat of a built-in thermostat in some ways. Whether the world that we are creating is going to be adequate for human needs, I think is the real question that we would need to ask ourselves, because we see in all of these mass extinctions a pretty broad wiping out of a lot of organisms, like a lot of organisms. We're talking the vast, vast majority of species in all of these mass extinctions getting wiped out. Are we okay with that? And are we creating an environment that humans can live in? The Earth, I think, is going to survive just fine. Evolution will go on to create replacement organisms when things calm down. But if we would like to survive longer, we've got to make some hard changes. So I think I've already forgotten the second part of that. So was the second part about given the speed that we're working at? No, what was the second part there, Rob?
Well, just if are we headed towards another mass extinction event by
Oh,
our actions?
are we headed towards a mass extinction event? I think there is not broad consensus in the scientific community on whether or not we are in a mass extinction, but whether or not we are headed towards a mass extinction, I think if you ask that question, you probably would find broad consensus that unless we make some strong modifications to how we are behaving, that we are looking at vast changes to the way our planet works, and that we are looking at changes in what species can survive, what habitats are still around, and like I said, ultimately whether it's a habitable planet for humans. Some things are going to do just fine. Some things will not, and I'd hate to see us in that line of organisms that are not doing just fine.
Thank you so much for that incredibly thoughtful answer. Unfortunately, that is going to be the last question that we do have time for today. So I'd like to throw it back to you for some closing comments.
Hey, well, thanks everybody for coming on by today. I I obviously like talking about mass extinctions, and we had some really interesting questions at the end there. And what I take from mass extinctions is ultimately a message of hope, even if that hope isn't necessarily for me. I knowing that our planet has gone through these major shifts in its previous history, and we've seen all of the beauty that has come out of these shifts. Um, Always brings me a sense of hope for both like the past and the future, and knowing that the more things change, the more things are going to change again. And that if we hadn't had the extinction at the end of the Triassic, we would not have had dinosaurs, and your 6-year-old would not have gotten to talk to you for hours on end about dinosaurs. So thanks for coming by today and looking at a geological timescale view of some of these massive perturbations that have happened in the planet over the years.
Eleanor, thank you so much for taking the time to present for us today. And I'd also like to thank everyone who joined us. So if you are interested in information on how you can travel with NatHab, please give us a call at the number on your screen, or you can send us an email at info@nathab.com. Our adventure specialists are happy to help you out. Join us tomorrow for our next daily dose of nature. You can check out this week's lineup, including registration links, on our website at nathab.com/webinars. We did record today's presentation, and we will have the replay available on our website soon. With that, I will conclude today's webinar. Goodbye, everybody. We will see you next time.